All right. Well, let's go ahead and get started. We got a lot of ground to cover today. By the way, I was looking on YouTube and I didn't notice any recording for Thursday. Do you remember if I made one? Like, did I have the microphone on Thursday? Anybody remember? I've had some technical problems getting it from here to YouTube sometimes, so I'll check that machine to see if it's there, but there may be a missing lecture, so we'll see. Hopefully that's not the case, because I'd like to have all of them. Looks like I've got everybody's homework 9 here. Your next homework assignment is going to be due a week from today, and that's also the day that we're having our second midterm exam. The coverage for exam 2 is going to be chapters 10 through 12. And like the first exam, you'll be allowed to bring the equation packet that I've given you and one extra page. Yeah, front and back. For the project submission that's due on Thursday, I've got a video there where I explain how to print from water gems. If you're having trouble, then you can refer to that. It goes through the process of scaling it so that you can actually see the annotations and how to print to a PDF if you've never used a PDF printer before. It's pretty straightforward, but if you would like the help, I do have that recording there. Yeah? Mm-hmm. 5 meters in diameter? Yeah, that would be probably too big. Yeah. I don't expect that anything will be larger than the pipe sizes I've given you for the costs. You know, like I've told you the range of costs for a lot of different pipe sizes. Yeah. Any other questions real quick? Because we don't have a lot of time to talk about the project. If you do have questions on the project, like detailed ones, I'm happy to go over that with you in my office after class or during my office hours. But did you have a quick question?
I don't know how quick.
All right. Yeah, maybe we can address it after class because, all right, we've got a lot of stuff to cover today with chokes, enlargements, and contractions. Any general announcements, questions, or things related to scheduling? All right. So this is where we left off last time. We were looking at what happens when there's a drop down, and that's pretty straightforward. You know, the depth is going to change depending on whether it was subcritical or supercritical upstream. But what's a little bit more complicated is the step up. And the step is more complicated because there's some maximum step that could be too tall, and it could begin to choke the flow. And so if we had subcritical flow upstream, then the flow will stay subcritical downstream, and the depth is going to decrease. And a bigger step means that the depth downstream at 2 decreases even more. And this is just a review from the previous slide, trying to refresh your memory of where we were at. And then there's some maximum step height, the critical delta Z. And we know that the biggest step that can be handled by the flow without choking this upstream section is the step that's going to cause the critical depth after the step. And you'll remember that the critical depth, what makes it unique and special, among other things, is that happens to be the depth that's the most hydraulically efficient. That's the depth where we're able to carry the most flow for a certain amount of specific energy. And so what I'm defining as efficient is most flow capacity for a certain amount of specific energy. And remember that specific energy is energy measured above the bottom of the channel. And so there are a couple of things that we know about flow at the critical depth is that when we've got critical conditions, the depth is 2/3 of the total specific energy, and the velocity head is 1/3 of the specific energy. Now if we make this step, the step height bigger than the critical step height, and that's what's at the bottom of the screen there in option D, we've made the step so big that now the flow is going to choke. And so we introduced the idea of there being a Y'1. And the Y'1 is meant to indicate the depth upstream after choking, when it's come into a second equilibrium. And that's what we're going to be taking a look at today is several examples that illustrate how to calculate what the new depth is going to be after choking, how to calculate what's the maximum step height that we can allow before choking occurs, and things related to this idea of a maximum step. So any questions so far on this review slide here?
Choking where it had to just build up.
That's right. Yeah, the water depth had to get deeper upstream in order to gain and accumulate enough energy to get over the obstacle. You know, at first, when this step got really tall, there wasn't enough energy here to get over that obstruction. And so the way that it deals with that issue is it gets deeper and deeper, and as it's getting deeper, energy is accumulating because of the added depth, and then finally there's enough energy at one to get over that obstacle. And when it finally has enough energy to get over that obstacle, then you'll notice it's flowing at the critical depth. The depth will only accumulate upstream of the obstacle until there's just barely enough energy to get over that obstruction. And the most efficient depth to flow at in terms of minimum energy for maximum amount of flow is the critical depth. And so it will stay at the critical depth. Any depth that we make it deeper and deeper and deeper, it'll just continue to flow at the critical depth.
So the only way it would go back to being like more than the critical depth is if like the flow rate increased upstream.
Yeah, that's right. Or if we made the step lower. All right, so what's the name of this? Not this one. What's the name of this one?
Specific energy curve.
Specific energy diagram, right. And the specific energy diagram on the horizontal axis has specific energy, and on the vertical axis has the depth of flow. And who can remember what we used this for? What was the purpose of this curve?
Critical depth and tell subcritical
All right, there's a lot of information we can draw. We can find out what the critical depth is. We can find out, you know, what is the depth that distinguishes subcritical flow, which is above that line, and supercritical flow, which is below that line. It's also useful because we can find, if we know, you know, our flow depth is y1, we could find out what's the alternate depth. And the definition of the alternate depth is some different depth. You know, this was a much lower depth, some different depth with the same amount of specific energy. Any crossing with the same vertical line is going to have the same amount of specific energy. And so there's two possible depths that have the same amount of specific energy, a subcritical depth and a supercritical depth. And so we use this specific energy diagram to help us find whether conditions are supercritical or subcritical at a certain location, help us to know the alternate depth, and also, as illustrated here, we can find out what the new depth is going to be if there's a certain obstruction, if there's a step down or a step up. And when it was a step down, we would shift to the right because we were gaining energy. And if it's a step up, like the obstructions pictured here in this sequence, if it's a step up, then we shift to the left on the specific energy diagram to find the new depth. Okay, that's important to remember, that a step down is you're looking to the right because you're gaining specific energy, and if it's a step up, you're losing specific energy, which is leftward on that on the horizontal axis. Okay.
Well, we have, like on the exam, we get access to Excel.
I'm not sure. I haven't written the exam and don't know whether there will be an Excel question. I'll have to get back to you on that.
The only way I could do it with the homework was with the channels not being square. There's too many groups to solve in the calculator. We had to do it through Excel. We'll come out on iPad. I just found the minimum. I just used some solvers.
Yeah. Yeah. If I didn't let you use Excel on a problem like that, I probably wouldn't give you a trapezoidal channel. But I'll try and remember to look at that and get back to you on Thursday. All right, so here's where we're at today. We're going to look at an example to try and find out what is the maximum step. We'll go through the calculations to find for this rectangular channel, how big of a step up can we tolerate before the choking flow occurs, before it actually starts to make the depth of water upstream get taller. So this is kind of like a before and an after, or you can think of it in terms of downstream and upstream. Either one works. Here at situation 1, which is prior to any sort of an obstruction put in place, we've got a rectangular channel. The flow rate's 4.25 cubic meters per second, and we can see the dimensions of the channels 2.5 meters wide, and the depth is 0.9 meters. So we want to find out how tall, if we put in a step that's all the way across the bottom of the channel, how tall could it be before choking occurs? In other words, what's the maximum step height? So the first thing we're going to do is just find some parameters about what's going on at location 1. And we can do that by, we know first of all that both the bottom width and the top width are 2.5 meters. Our flow depth prior to any sort of an obstruction is 0.9 meters. The flow rate, 4.25 cubic meters per second. And then we can find the velocity at 1 by Q divided by A1. All right, the velocity at 1 is 4.25 cubic meters per second divided by the cross-sectional area, which is the 2.5 meters of width and 0.9 meters of depth. And so the velocity is 1.889 meters per second. Pretty straightforward so far. We'll also calculate the flow per unit width, lowercase q, which is the q divided by the channel width. It was 4.25 cubic meters per second, and our channel width is 2.5 meters. So the flow per unit width is 1.7 meters squared per second. All right. When the flow is just starting to get choked, what do we know about the depth of flow over the obstruction when choking just barely starts to occur? It's the critical depth. So what I'm asking you to remember is that just when we've just barely got that maximum height, its critical depth is over the obstruction. And so by definition, in this problem statement, when I'm saying what's the maximum obstruction height allowed before choking, let's say at choking, just before the choking occurs, like the depth of flow over that obstruction is going to be the critical depth. And so we're going to say let Y2 equal the critical depth, because that is by definition the flow depth just before choking, or you could say at choking, but it's right on the border. And so since we know that Y sub C is for a rectangular channel only, the flow per unit width squared divided by G to the 1/3 power, we can calculate that the critical depth is 0.665 meters. So that will be the flow depth over the obstruction. Now we can find out what will be the velocity at that location, because we know the Q and the A2. Okay, the flow rate's still going to be 4.25 meters cubed per second. And now the cross-sectional area for the flow will be 2.5 meters, which is the width, and then the flow depth of 0.665 meters. Okay, that gives us 2.555 meters per second. So we know the velocity at 2 just before choking. And so now what we'll do is apply the energy equation. We'll say that we've got Y1 plus V1 squared divided by 2G is equal to the critical depth plus V2 squared divided by 2G plus this delta Z max. So we're just applying the energy equation. It's a pretty low-risk thing to do. It usually applies. You can rarely go wrong by trying to apply the energy equation. And let's just substitute in the values that we've got here. We've got 0.9 meters is the depth before the obstruction is put into place. And we've got this 1.889 meters per second velocity upstream, squared divided by 2G, is equal to the flow depth, 0.665 meters of depth, and we'll put in our velocity, 2.555 meters per second, squared divided by 2G, plus the delta Z max. Okay, so we calculate each of those terms. It turns out that the delta Z max is 0.084 meters. Anything bigger than this, then there won't be enough energy at 1 to get over the obstruction. All right. So what's the twist in this problem? What's the trick? You know, like if this was a quiz question, what do you suppose would be the number one mistake or the number one problem that would trip people up? No? Forgetting what? Okay, maybe just doing the energy equation without the Z max. That could be it. I think that the number one mistake would be forgetting that the critical depth should be used at 2. I think that that's sort of like, that's the linchpin that everything depends on, remembering that before choking occurs, that means like that incipient condition just right before choking begins, it's going to be the critical depth. So let Y2 equal YC. I think this is the trick in the trick question. All right? So if you're going to highlight something, highlight and remind yourself why we made that assumption. And if we go back to the specific energy diagram, we remind ourselves that it is the critical depth that we've got. Y2 is the critical depth when you've got that biggest delta Z that can be tolerated. All right. Any questions? Yeah. Yes. The choking will make the depth upstream large until it can reach up and achieve that critical depth. Supercritical? Because, why does it go for the critical depth? Because the critical depth is the one that's the most efficient at conveying flow. And the energy is not going to build up to any, it's not going to give away more energy than it needs. And so it's the critical depth that can get that flow rate over the obstruction with the lowest amount of specific energy. So it won't go beyond that. All right. So again, choked flow is where we've gone beyond some maximum constriction. The maximum constriction causes critical flow at the constriction, whether it is a channel width changing, or in the cases we've looked at so far, a step up. We go beyond that, then the sequence of events is that the water upstream will pool, and then when there's enough energy upstream of the obstruction, then finally the water will flow at the critical depth over the obstruction. Now, since you're increasing the depth upstream, you may cause damage to structures. This in D, the water level went up. So it could be homes or businesses. There could be a lot of different things between the normal water elevation and the now higher water elevation. So if you think in practical terms, an obstruction like this could be sediment accumulating in a channel. It could be something falling into the river, and so you have to be pretty sensitive when you are a hydraulic engineer to changing the water surface elevation upstream. Ordinarily, that's just not tolerated at all. You have to prove anytime you want to put in a culvert or make any kind of a change to the channel that you're not going to increase the depth upstream. Don't want to affect the headwaters. All right. So let's consider another possibility. Let's say that we've got 10-foot deep water. Water's flowing along a channel, and there's an obstruction that is also 10 feet deep. So obviously, if the obstruction is 10 feet deep and the water flow is 10 feet deep, it's going to have to pool to get over that obstruction. I didn't quite draw that to scale, did I? Because here's 10 foot of flow, and here's the 10-foot obstruction. I'll do better next time. But you can imagine, use your imagination, that those are both the same height. And so what we know is the water will pool upstream, so y'1 will increase until there's enough energy upstream to get critical flow over that obstruction. It's not going to get any deeper than is required to just barely have enough energy to get critical flow over that obstruction. So let's go through that process. Let's say, what if we had 500 CFS, the channel width was 10 feet, and we had an initial flow depth at 1 of 10 feet. What will be the new y'1? And y'1 is the new depth after pooling. So we're going to go through this process of finding how much energy is required to get over the obstruction, and we'll compare how much energy is needed to get over to the obstruction with how much energy is available. So we'll do this comparison. We'll prove to ourselves that choking is going to occur. I mean, we can just look and we know choking is going to occur because the obstruction is the same depth as the water surface. But numerically, it won't always be that obvious. And so the way that you compare is you look at the available energy versus the required energy. And then after that determination, then we'll find the new upstream depth to satisfy the required energy. All right. Yes, this is a rectangular channel. Okay, so we've got Q is 500 cubic feet per second, and the channel width is 10 feet. The initial depth of the water is 10 feet, and we want to find what is y' of 1. And so a first step in problems like these is to find the critical depth, and it's easy to do when it's a rectangular channel, and only when it's a rectangular channel is when we would use this particular formula. If it wasn't a rectangular channel, what formula could we use to find the critical depth? The Froude number equation we'd set to 1. That's right, and we'd solve for the unknown depth. Okay, but in this case, things are easy. We have 500 cubic feet per second divided by 10 feet is the channel width, and so that gives us the flow per unit width, lowercase q, 32.2 feet per second squared is g. Let's find the 1/3 power of that, and we can calculate that the critical depth is 4.265 feet. All right. And so from that we can find E min as 3/2 of the critical depth. And so that is 6.398 feet. And just to refresh your memory, what I mean by the minimum energy is this is the this critical depth is the flow depth that's the most efficient. And you'll remember that when you have critical flow, that the depth is 2/3 of the specific energy and the velocity head is the other 1/3 of specific energy. So that if you know the critical depth, you can find the specific energy by doing 3/2 times the critical depth. And so in other words, what this is the energy, I should say specific energy, when flow is critical. This is how much energy we absolutely, the bare minimum that's required to get the flow over that obstruction. There's got to be at least that much energy. Plus the obstruction itself.
And that's true for all types of channels?
Well, this 3/2 only works for a rectangular channel. Yeah. Yeah. All right. So, so then the total energy required for this obstruction is going to be the specific energy that exists in the flow plus the delta z of the obstacle. And so it's going to be the 6.398 feet plus the 10 feet of the obstacle itself. And so we've got to have 16.398 feet of energy total. And we can look at how much available energy was there. And so the total energy initially available before pooling okay, that's going to be just basically E1, so that would be Y1, the flow depth, plus the velocity head. I'm going to show you a new way to calculate the velocity head. You know, we already know that you can calculate velocity head by v squared divided by 2g. What's another way? Good? That's right. Well, here's the new way. It is lowercase q squared divided by 2g y squared. And so we're talking about y1. So it's the flow per unit width instead of the it's actually the same thing as this if you think about it. Q divided by b gives you lowercase q, and area divided by b just gives you the depth. And so it's just dividing both the numerator and the denominator by the width of the channel. All right? And so what we had was 10 feet was the initial flow depth, and then we have a flow per unit width of 50 feet squared per second, squared divided by 2g and then the depth of flow 10 feet squared. Okay, and you know this velocity head term is 0.388 feet, and so the total energy is 10.388 feet required. Okay, so will there be choking? You know, visually we know that there will be choking just because you've got a 10-foot obstacle and 10 feet of flow. Numerically, the way we've proved it to ourselves that there will be choking is we found out that there's going to be approximately 6.4 feet of energy just in the flow itself. And then we've got to have another 10 feet of energy to get over the obstacle. So this is how much energy there's going to be at 2. You know, at 2 is going to be the flow, the energy in the flow and the energy of getting over the obstacle. This is along the same lines of what we've been doing before. Like over here when we were looking at, you know, the energy at 1 and the energy at 2. So what we're saying is that the energy at 2 is going to be this, and this represents 2/3 of this is the depth, 1/3 of it is the velocity head, and then here's the delta z. And so that's the same thing as we had over here. You know, over here we had the delta z, the flow depth, and the velocity head. Those were the 3 things that went into how much energy there will be at the downstream location. So combining the two, to get over that obstacle, we need to have 16.4 feet of energy, but at 1, initially, before any pooling occurs, there's only 10.4 feet of energy, and so since the available energy is less than the required energy, pooling will occur. And so we're going to say required is greater than available, so pooling will occur. Where? Here? Oh, yeah, thank you. Yeah, that is available. Thank you. That was a mistake. Yes, it should say available. Okay. So, good question. So, Andrew's trying to figure, you know, how are we going to calculate y1 prime? What do you think we're going to do to find y1 prime? It's not going to be as simple as that. You're on the right track. What we'll do is we will set this equal to the energy, and then we're going to have some unknown y and some unknown velocity head, because remember there's also the velocity head that changes when the depth does. We're going to write the velocity head in terms of y prime 1, this unknown depth that it must pool to. But so let's just take a step back to this statement where required is more than what's available. And so what's available is going to increase through pooling until available equals required. And then the pooling will stop because there will be enough energy. You don't have to continue to have the water level get deeper and deeper anymore because there's finally enough energy there to get over the obstruction. So that's when pooling will stop. Any questions so far about all this? Okay, let's follow through with the final part of this problem and calculate what will be the new upstream depth after pooling. All right, so new depth. Y prime of 1. All right, what we'll say is that the E required is going to be equal to y prime of 1 plus q squared divided by 2g y prime of 1 squared. So the depth at 1 will be whatever it takes for us to have that required energy. So it'll be 16.398 feet is equal to y prime 1 plus the 50 feet squared per second squared divided by 2 times 32.2 feet per second squared times the y prime 1 squared. Okay, if we rearrange that, that is 16.398 is equal to y prime 1 plus 38.820 divided by y prime 1 squared. And the cubic equation that we'll get is y prime 1 to the third power minus 16.398 y prime 1 squared plus 38.820 is equal to 0. Okay, and we can find the roots of a cubic equation like this. Y prime 1's roots are negative 1.474, 1.621, and 16.251. And so obviously the flow depth upstream will be negative 1.474 feet, right? No. It will be that the water depth increases to 16.251 feet. And besides the fact that it's obvious, if pooling is going to occur, it's going to go from 10 to 16. It's not going to go from 10 to 1.6. The other reason that we know that is that our critical depth, if we recall, the critical depth was 4.265. And so originally, before pooling, we had 10 feet. And so before this choke occurred, the flow was subcritical, and so it's going to stay subcritical after it goes through the pooling process. So that's just another way that we can feel comfortable with this being the correct route, is by comparing the flow before to the critical depth. Okay, so what's the trick to this problem? You know, if this problem was a quiz question, what's the thing that would trip people up? What's the tricky part? Oh, okay, so confusing the depth with the energy? All right, yeah, that could be one thing. I see. Yeah, confusing the energy with the depth itself. Yeah. Remember that the depth is only one of the two components of specific energy, the other being the velocity head. All right. Any questions about this before we move on to another example? Well, let's say we've got the same basic conditions. We've got the same channel carrying the same flow rate. Well, will it choke if we've got the 3-foot obstruction? We saw that it definitely choked when there was the 10-foot obstruction. What about if it's a 3-foot obstruction? Will it choke? Well, what we looked at before was the available energy, right? And what we found with the available energy is there's 10.388 feet of available energy. And if it was going to be choking there, then we'd have the critical depth and the 3 feet. So the critical depth was, let's see, the minimum energy, which is the critical depth and the velocity head, of 6.4 plus another 3. My prediction is that we are going to be okay. Just by looking at it, by saying from our previous problem that we worked when we had 10.4 available, and the amount required is going to be the delta Z and the E minimum, where the E minimum was 6.4 and the delta Z is going to be 3, so that gives us 9.4. I think that what's available is going to exceed what's required. But let's go through the formal steps of that and just double check. And when we finish this example, then we're going to work on when the channel changes width, which actually is a lot. The channel is always changing width, so it's an important one to be able to handle. All right, so will it choke when we have delta Z is equal to 3 feet? Okay, so previously we knew that the critical depth is 4.265 feet. We calculated that in the previous example. And we also know that we have the energy at 1 is equal to the energy at 2 plus the delta Z, because it is a step up. So the energy that's at 1 is going to be reduced, the energy at 2 is going to be reduced by the delta Z compared to the energy that was at 1. We could rearrange that to look like, another way we could write that is E1 minus delta Z is equal to E2. Or, in other words, Y1 plus V1 squared divided by 2G minus delta Z is equal to Y2 plus V2 squared divided by 2G. Okay, or in terms of the flow rates, it could be Y1 plus Q squared divided by 2G A1 squared minus delta Z equals Y2 plus flow rate squared divided by 2G A2 squared. Okay, and the reason why it may be convenient to express it like that is that we know that we're going to have the flow rate is 500 CFS, and so let's substitute in all of the numerical values that we've got. 10 feet is the flow depth at 1, and the 500 cubic feet per second squared divided by 2 times G, and 100 square feet squared. And remember that the channel width is 10 feet and the flow depth is 10 feet, and so that's where this 100 feet of cross-sectional area is coming from. And now we've got the delta Z is 3 feet, and then the unknown flow depth, Y2, because we don't necessarily know what the flow depth is going to be over that obstruction. And then plus the 500 cubic feet per second squared divided by 2 times 32.2 feet per second squared, and then 10 times Y2 squared. So the energy at 1, the obstruction height, and the energy at 2. Okay, that is 10 feet plus 0.388 feet minus 3 feet is equal to Y2 plus 3882 divided by 100 Y2 squared. We can combine things together and we'll get 7.388 is equal to Y2 plus 38.82 divided by Y2 squared. And that leads to the cubic equation, Y2 cubed minus 7.388 Y2 squared plus 38.82 is equal to 0. And then we'll get 3 roots, negatives 2.03, 2.961, and 6.457 feet for all of them. And so we know that it's going to be the subcritical root. This will be the new flow depth. And so it won't choke. Choking will not occur. All right. Any questions? All right, well, let's move on to the other way that choking could possibly occur besides an obstacle going in the bottom of the channel, is what if the channel itself was made more narrow? Now, here's an example of how that could happen, is if some sort of an obstruction is put into the channel, it's effectively made it more narrow, because if you think about upstream, the channel, the channel has this entire width of the stream, but now if you put in a lot of piers, the flow can't go through these concrete piers, and so now the cross-sectional area has been reduced, because now the cross-sectional area in the vicinity of the piers is just how much area is between them in each span. And so will the water level rise or fall because of that constriction? Yeah, it kind of does look like it fell. Now that might just be an illusion because maybe the water depth increased at the upstream face of that. But what we're going to do is go through the calculations and try and find out in what cases the water depth decrease when the channel gets more narrow, and when will the water depth increase when the channel gets more narrow, because there are cases in which it'll go one way and cases in which it'll go the other. Just like when there's an obstruction, you wouldn't have guessed necessarily that, let's go back to this series of drawings, you wouldn't have guessed that the depth would be getting more shallow by the obstruction, right? That was a little bit counterintuitive here, that as this delta z gets bigger, that made the flow depth over the obstacle get smaller. So that's just as one illustration of how sometimes these flow depth responses to channel modifications can be counterintuitive. And so a constriction can be both when there is a step in the channel, like we've already looked at, or it can be when the width of the channel decreases. Now think about flow per unit width. Remember, lowercase q is big Q divided by b, the width of the channel. And so when you make the channel narrower, that means you're going to have the same flow rate, the same big Q, but now a smaller b. And so that increases the flow per unit width. But the energy is going to be the same. The specific energy doesn't change because the channel bottom isn't going up or down like it did when the bottom of the channel is raised. So here's an illustration of a wide channel that necks down to a smaller, more narrow channel as the flow meanders through different types of conditions. And the behavior at the constriction is governed by what happens upstream. And we have to look at whether it's subcritical versus supercritical, because in the same way that that was important when we were diagnosing what happens with the step, we also have to know the supercritical or subcritical, the flow regime of the upstream flow when we're looking at a change in the channel width. And if you have subcritical flow upstream of the constriction, then you're still going to have subcritical flow after the constriction. And we'll go through this process and we'll be finding routes again, and we'll have to know which of the routes to select, and the way that we'll know which of the routes to select is because we'll know whether we were subcritical or supercritical before this narrowing or widening of the channel. And so let's just take this same 2.5 meter wide channel that we looked at earlier today, where we had 2.25 cubic meters per second of flow, and the flow depth was 0.9 meters. But what now if we put in a couple of piers? And so now the effective width of this isn't 2.5, because if both of these piers are 0.25 meters in diameter, then together the two of them, 0.25 times 2 is 0.5 meters in width. And so now the flow can only go through 2 meters of width. So the actual lowercase b is going to be 2 meters. And so our flow per unit width changed here in this example. And we're going to want to find out what's going to happen to the flow depth because of this obstruction. All right. We're going to say that the energy at 1 and the energy at 2 are equal, and therefore the y1 plus v1 squared divided by 2g is equaling y2 plus v2 squared divided by 2g. Since we have a rectangular channel, we know that the flow per unit width is going to be upstream, before the constriction. The y sub c was 2.25 cubic meters per second divided by the channel width of 2.5 meters. So that's the flow per unit width, squared divided by g, and then all of that to the 1/3 power. And so the y sub c upstream of the constriction was 0.436 meters. All right. And what we have is the flow is going to be greater than that, since y1 is 0.9 meters. That's greater than y sub c, 0.436. So flow upstream is subcritical, because the depth is greater than the critical depth. That's subcritical. All right. So we can find the velocity at 1 is going to be the flow rate divided by the area at 1, 2.25 cubic meters per second, and the area is 2.5 meters of width and 0.9 meters of depth, so it's 1 meter per second is the flow velocity at 1, and therefore the energy at 1 is the depth at 1 plus v squared divided by 2g. So it is 0.9 meters, which is the flow depth, and 1 meter per second squared divided by 2g. So it is 0.951 meters. So what we're going to say is that 0.951 meters is the same amount of energy that there will be at 2 after the obstruction. And the way that we're going to express the velocity head at 2 is going to be in terms of q squared divided by 2g a squared, because our flow depth y is still unknown. So it'll be y2 plus 2.25 cubic meters per second squared divided by 2g, and then the area is going to be 2 meters of width times the unknown flow depth y at 2 squared. So it's important to recognize that, the whole width of the channel is 2.5 meters, but each one of these is a 1/4 meter wide, and so together that takes away 1/2 meter of effective flow width, and so we've only got 2 meters of flow width. And so the new cross-sectional area is going to be whatever the depth happens to work out to times the 2 meters of effective width. Okay, and so this is y2 plus 0.6451 divided by y2 squared. So the equation is 0.951 y2 squared is equal to y2 cubed plus 0.06451. So that is y2 cubed minus 0.951 y2 squared plus 0.06451 is equal to 0. And so the roots, and there are 3 of them, one of them negative that we can immediately reject. The supercritical root and the subcritical root. And we select the subcritical root because we already found that the conditions upstream of the obstruction were subcritical, and so the new flow depth after the obstruction will be 0.865 meters. So it was 0.9 meters, and it actually got shallower, which is another thing that's counterintuitive, that if you've got a channel and you put in obstructions, that instead of, you'd maybe think that putting an obstruction is going to somehow back it up and make the water get deeper, but actually the response here was that the water depth decreased. How is that possible for the water depth to decrease? What has to happen with the velocity there? The velocity has to increase to maintain continuity, because remember that the overall flow rate isn't going to change, at least not in this case, because we haven't choked the flow. So y1 is equal to y2. And so it sped up, basically. What we can say is that the water velocity increased to get through this section where there's obstructions. And as it increased the velocity, the depth decreased slightly. It's not a big change here, but it would be measurable. Any questions about how to handle Peirs like this? Okay, here's a top view of what another type of contraction could look like. This is the same as putting Peirs into the water. You're effectively decreasing the width of the channel. Now here B1 is greater than B2. And there's a transition where we gradually change the flow, the channel width, and they'd have a gradual taper like this to try and cut down on energy losses. You know, there is sort of a local loss that occurs in a transition because you're inducing turbulence when you change the channel profile. As long as it's a rectangular channel, we can calculate the critical depth according to this formula. And it's important to take a look at the specific energy diagram. The specific energy diagram actually moves. Rather than using the specific energy diagram that we had before where we're just at different locations on the diagram, here, if you've got a greater critical depth, then that means it's going to raise the specific energy diagram for the contracted flow, and it's also going to shift it to the right. And so here's the first specific energy diagram for the flow condition at 1, and then the flow condition at 2 when the channel got narrower. If you make the channel narrower, that shifts the specific energy diagram up and towards the right. And it shifts it up and to the right for the same reason, because we know that the critical depth is a function of the flow per unit width, and so lowercase q increases when you decrease this parameter b. You know, if b gets smaller, if the channel width gets smaller, then that increases the flow per unit width, and if the flow per unit width goes up, then so does the critical depth. And so you'll notice that here the y prime is bigger than the YC, you know, the prime critical, so the critical depth after the constriction is greater than the critical depth before the constriction occurred. And so that's why it's higher. And it's to the right because E minimum is simply 3/2 of the critical depth. So the two go hand in hand, up and to the right. Okay, so let's put some numbers into this contraction. What if we have a channel that is 10 feet wide at the first location, has a depth of 5 feet, and a velocity of 3 feet per second? So I'd like you to actually work on this one, maybe with a partner. Try and find out what's the minimum width of the channel that could be used to avoid choking. So how far can we taper that down and still be okay? What can we get away with a minimum B2? And so the trick here is going to be that we assume that it's critical conditions. So you'll have the critical flow at 2. Like I said, feel free to collaborate with your classmates. Try and find out what is the minimum width, B2, that could be used to avoid choking. Okay, we can start off by calculating the total energy at 1. We know that the energy at 1 is going to be the depth and the velocity head. So that's going to be 5 feet plus, in this case it's at V1 is 3 feet per second. That's Q divided by A1, which is it's given directly, yeah. 3 feet per second is given directly. So we can just put that in 3 feet per second squared divided by 2 times 32.2 feet per second squared. Okay, so the energy that's at 1 initially is 5.140 feet. And now the smallest B will lead to the biggest Q for some certain Q. Okay, so we've got a flow rate, and we're going to try and make B2 progressively narrower and narrower until we've got the biggest flow per unit width that can be handled. And now the E minimum at 2 is 5.140 feet. That's basically when we've got the minimum energy, and we know that the critical depth is going to be there. And so it's known to us that the critical depth is 2/3 of E minimum. And so it's 2/3 of 5.140 feet. And so the depth of flow at 2 is going to be the critical depth, and so that is 3.427 feet. So I guess what we're saying is if we want to keep making B narrower and narrower and narrower, the depth is going to be decreasing and decreasing and getting shallower and shallower. And the extreme of that is before we start causing choking, the depth after the constriction will be the critical depth. And so here's the critical depth that we'll eventually get to. And if that's the critical depth, then the velocity head, we know that the velocity head, V2 divided by 2g, is going to be the leftover amount between the minimum energy and the flow depth. And so we can find that the velocity at 2 is going to be 10.5 feet per second. Now all of this is just based on our knowledge that we're going for an extreme. We're going for the narrowest channel we can, and when we've got that really narrow channel just before choking, it's going to be the critical depth in there. And so this is the total energy. The 5.4 is the total specific energy. The 3.4 is the depth component of it. So what's left over is the velocity head. We solve for V. That's 10.5 feet per second. And so for Q is 150 cubic feet per second, then A2 is going to be Q divided by V2, and so that is going to be the 150 feet cubed per second divided by the velocity, which is 10.5 feet per second. So that means the cross-sectional area has to be 14.28 feet squared. And if we know what the depth is going to be, because we know that the depth will be the critical depth, then we can find the width. So in other words, the area is going to be the critical depth times whatever this width is that we're trying to solve. And so B2 will be the area at 2 divided by the critical depth. And so that'll be 14.28 square feet divided by the critical depth of 3.427 feet. 4.17 feet is the narrowest we can go. And any narrower than this, and the flow will choke. So this problem is very much similar to the type of problem when we're trying to find out the maximum obstruction. Where we're trying to find out how tall could this step be. That's the same kind of problem as saying how narrow could the channel be after a constriction. Because in both cases, the trick to solving it is knowing that you'll have the critical flow right at the point of choking.
Does that mean instead of having gradually those, you just go basically take two walls and shove them in?
Yeah, instead of a transition if it was abrupt?
Well, it's still
Well, when we have something abrupt rather than gradual, then there's going to be an energy loss between them. And so you see how there's this term in the energy equation, which is a loss coefficient times the velocity head. If we had a really abrupt transition and it was a contraction, we'd probably have to use 0.6, on the high end of that scale. And so so far we've been neglecting energy losses in an expansion or a contraction, but really we can account for them, and this is how. And so if you had it abrupt rather than gradual, it would, there'd still be a limit at which any narrower and it's going to start to choke. It's going to change that width because of what C value you use in the energy loss term. So just before we finish for today, let's look at what happens to the specific energy diagram in an expansion. Okay, so here's our original specific energy diagram. What happened when, when the channel got narrower? It went up and to the right, so it looked like this. Okay, so here was our original YC, and here was our original E minimum when we 2 is when the channel got narrower. it went up and right. What do you think is going to happen when the channel gets wider? Good guess. And that's exactly right. It goes down and left. And so 3, wider, it goes down and left. And the reason for that is that the flow per unit width is going to be decreasing. So this is where we'll pick up when we get together on Thursday. Let's just take one final look at the announcements. Remind ourselves that you are supposed to be finishing up your draft submission for pipe network sizing. Just upload that to MU Online before class next Thursday, this coming Thursday, in 47 hours from now. And if you have any trouble making your PDFs, you can refer to that video or stop by my office hours. I'm happy to try and help you out. But I will see you on Thursday.